So let's get back to this complex wave function, but let's think of the particle in the box now. So we're going to have a wave function equal to the square root of 1 over L times e to the I n pi over L times x. Okay, that's the slinky function that we were talking about in class on Friday. And now, we already noted in the previous lecture that this thing looked a lot like the particle in the box. I mean, that n pi over Lx just looks a ton like the particle in the box. And we've got a square root of something over L for the particle in the box sine wave function. It was square root 2 over L. This one's square root 1 over L. And then there's that I hanging out in the exponent of the exponential function, but it really looks a lot like the particle in the box. So in fact, you might recall there's a thing called the Euler relation that says sine of kx is equal to 1 over 2i, another annoying imaginary number, but whatever, times e to the ikx minus e to the minus ikx. And we can use that. So that's why the slinky function, e to the ikx, in this case, looks a lot like sine. It is a lot like sine. And we can just tweak it a little bit like this and take what we call a linear combination of two functions, and we get sine. So we can express sine as this funny combination of complex functions. So take a look at this. You notice that if I set x equal to 0, I get e to the 0 minus e to the 0, 1 minus 1, and that works. So that's 0, which is what sine is at 0. And also, if I go to some multiple of n times pi, then I'm going to get the same thing. So if kx equals n pi, I'm going to get e to the I n pi, which is 1, minus e to the minus I n pi, which is 1 or minus 1, basically, for n equal 1, 2, 3, 4, 5. So those work too. That'll still be a 1 minus 1. So this thing does go through 0 as needed, basically. So it looks a lot like sine. It's plausible that it's sine. It obeys the boundary conditions, especially for 0 and L, and that's all we have to do. Any function I can make that is an eigenfunction of the Hamiltonian and obeys the boundary condition is a reasonable is a solution to the Schrodinger equation. And so this thing I cooked up does that, or at least it's plausible that it does that. We're going to prove that it does that in a little bit. So that seems like a kind of a reasonable deal. If we obey the boundary conditions, we're all in good shape. So let's start doing some algebra, start pushing some things around here. So using Euler's relation, we have root 2 over L sine n pi over Lx is equal to 1 over 2i times root 2 over L e to the I n pi over Lx minus root 2 over L e to the minus I n pi over L times x. Okay? That's just Euler's relation. Now I can pull out a root 2 and get root 2 over 2i times square root 1 over L e to the I n pi over Lx minus square root 1 over L e to the minus I n pi over L times x. That's equal to 1 over I root 2 times the square root of 1 over L e to the I n pi over Lx minus 1 over I root 2 times 1 over the square root of L e to the minus I n pi over L times x. So I just multiplied through by those coefficients, so I have two completely independent functions there, rather than having that root 2 over 2i kind of hanging out and multiplying the whole thing. The important thing about this is square root 1 over L e to the I n pi over Lx and square root 1 over L e to the minus I n pi over L times x. Those are both properly normalized slinkies. They're properly normalized wave functions over the interval 0 to L, over, in fact, for this function, any unit length of L. And that's an important thing, because that means that this function now is 1 over I times root 2 times the basis function we're going to call phi plus minus 1 over I root 2 times the function we're going to call phi minus, call it slinky plus and slinky minus. And the phi plus and the phi minus are properly normalized functions. So they're good, solid basis functions of the momentum operator. If you take the complex conjugate and you multiply that by the function, you integrate from 0 to L, you get 1. And so that's an important thing. So now we can write the particle in the box wave function. We can take sine, and instead of writing it as sine, we can say psi of x is equal to 1 over I root 2 times this phi plus of x minus 1 over I root 2, this function phi minus of x. So what? It's just sine. I've pushed and pulled and done all this stuff, and I've introduced a complex function to do them. What have I got? Well, the deal is, ask me about momentum. Remember the momentum operator? P hat operating on phi plus is equal to h bar pi over L times n. We worked that out last time. Times the wave function phi plus. And so that means the eigenvalue, h bar pi over L times n, that we get when the operator p hat operates on the function phi plus, is the value, p plus, the momentum, is h bar times pi over L times n. So again, p with the hat is a chewing thing. It's an operator. It's got a first derivative in it. Phi plus is this thing we call an eigenfunction, and that's the e to the I n pi over L times x. And then p plus is the eigenvalue that poops out of phi plus when we operate on it with p hat being the operator. So p plus is the eigenvalue, and it's a constant h bar pi over L times the quantum number n. Likewise, p minus, which the minus sign comes in, so it's minus h bar pi over L times n. It's a reason why we call these things phi plus and phi minus, and that gives us two different values of momentum. So if I use the momentum operator on the first part, phi plus, I get this p plus value, h bar pi over L times n. And if I use the momentum operator on the second part, I get a different value of momentum, p minus. It's just changing the sign. So instead of a positive momentum, I get a negative momentum. That means going forward, going in the positive x direction, versus going in the negative x direction with the same magnitude. So they have the same magnitude of the momentum, just opposite signs for these two solutions. So what we found is that we broke sine into two parts. We broke psi of x, which was just sine, into two parts. And those two parts individually have a well-defined momentum. Phi plus and phi minus have a well-defined momentum. So remember, we showed that sine itself, when we tried to operate on sine with the p hat, the operator, first derivative, we get cosine. We do not get a constant times the function. There is not an eigenvalue of momentum for the particle in the box wave function sine of n pi x over L. It doesn't work right. But we can break it into two pieces, and those two pieces do have a well-defined momentum. So here's one of these weird quantum things. It turns out that what happens if you go and you try to measure momentum is not that you get basically nothing. Remember how we ended the video of last time. If we ask this thing, what's your momentum, what's going to happen is we're going to get one or the other of those two answers, because we broke the function sign into those two, let's call it, phi plus and phi minus, forward-going and reverse-going functions. So we're going to get one or the other. So the momentum is going to be either h bar pi over L times the quantum number n, or minus h bar pi over L times the quantum number n, the positive value or the negative value with the same magnitude. So we're going to get one or the other of those values. So the momentum is going to be h bar pi over L times n, or minus h bar pi over L times n, the positive or negative value, going left or going right. Really going right or going left if we look at our x-axis in a normal way. And we're going to get one or the other of those answers. If we ask sign, if we ask the particle in the box, what's your momentum, I'm going to get one answer or the other. So the next thing I want to know is, if I'm going to get one or the other, how often? So, it seems like a game of chance. There's a lot of probabilities in quantum mechanics. And the answer is in those coefficients in front of remember I properly normalized. We made sure that the thing was properly normalized. So when the psi of x is equal to 1 over root 2 times I phi plus minus 1 over root 2 times I phi minus, those 1 over I root 2's are coefficients. So we can break this into a coefficient. We're going to go c plus times the eigenfunction phi plus, and then another coefficient c minus times the eigenfunction phi minus. And we kind of want to add them all up. So if any minus signs, we're going to collect them into the coefficient, and we'll see that they kind of don't matter in this probability game. And a postulate of quantum mechanics is the probability of finding a given answer is, for a coefficient n, is equal to that coefficient squared, the magnitude of that coefficient squared. And remember, that magnitude squared bit means you take the complex conjugate of a coefficient and multiply it by the coefficient. And that's going to deal with the fact that there's some imaginary numbers in this thing. So at the risk of being a little bit too repetitive, we've got the wave function psi of x is equal to 1 over I root 2 phi plus minus 1 over I root 2 phi minus. I've gathered everything in, so I'm adding coefficients. And if we take c plus complex conjugate times c plus, we get a half. It's 1 over root 2 times 1 over root 2, and basically with the complex conjugate in there, the I parts just take care of themselves. So if you kind of just don't worry about things that are multiples of I, or 1 or minus 1 or minus I, those are going to take care of themselves. And the same is true for c minus. C minus complex conjugate times c minus is equal to a half. So that's the probabilities. They're 50-50. And it's awfully nice that a half plus a half equals 1. So the probability of finding a momentum is 1. And the probability of finding those individual ones going left or going right is 50-50. So there's a 50% chance we're going to find the particle going right. That would be p plus h bar pi over L times n. And there's a 50% chance we're going to find the p, the momentum, is equal to minus h bar pi over L times n. And that would be the particle going left. And, just take very careful note of the fact that I took that square root 1 over L, and I made sure it stayed attached to the e to the plus or minus n pi x over L. And that was so that those phi plus and phi minus, what we call basis functions, were properly normalized. It's really, really important, because that by doing that, by keeping the normalization part of the deal carefully attached to my functions phi plus and phi minus, I get the right coefficients. If I hadn't have done that exactly right, then I wouldn't get the right probabilities because I would confuse the normalization part and the coefficient part. And there's always a good way of checking that. The way of checking that is when you're done, the probability of finding some answer, any of the answers, needs to be 1. And so you take the squares of all those coefficients, the complex conjugate times the value. You add all those up, and you better get 1.